Yeah, I am audible.
Yeah, you are audible.
Okay. I have to see how to share because Zoom always. Okay. Okay. Where to share these slides?
At the middle, you have this green option. Are you getting that?
Yes. Should I keep it to share the screen or?
Yeah, share. You can share. Once you click that, it will give you options that if you want to share one screen or the whole desktop and all that.
Okay. 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 Yeah. Okay. Thanks. I'm visible. I'm audible. Okay. Okay. I will try to share the slides. Yeah.
Okay, let me just quickly give an introduction to your talk. So Professor Narayanan is a professor at IIT, assistant professor at IIT Jodhpur. He works on this generation of entanglement photons and its application, laser matter interaction of optical design for large-scale solar fields and non-imaging optics. And he will be talking about generation and characterization of entangled photons produced by short pulses. It's to you.
Yeah. Okay. Yeah. Is it a full screen mode or?
Yeah, not yet.
Okay. Now?
Yeah, now, yes.
Okay. So, okay. Good morning. So thanks for the nice introduction. I would like to thank the organizers on this regard, QIQT. I also thank especially Professor Panigrage, who taught me at the University of Hyderabad, where I did my MPhil. Okay. So basically today I will briefly talk about some of the activities which is under the QEST at IIT Jodhpur, what we are doing. So this is basically a broader under the QEST umbrella, and we are generating the entangled photons using the short pulse lasers. So the generation and characterization of entangled photons produced via short pulse laser is my major talk, and also recently how I got introduced, and also some of the experimental techniques which someone is beginning or some of the graduates who are here online they can pick up or take it as a kind of introductory to their work. Okay. So basically my outline of the talk, so the entangled sources and its application, because especially last 1 decade or above, there is a lot of immense interest in this direction. And one of the things which I will discuss about is the SPDC using the short pulse laser. Followed by that, how do one characterizes this kind of an entangled photon by what is known as a quantum state tomography. So I'll briefly discuss about that. The essence of before doing that is basically one of the questions which came back in the late or during the Second World War by Hanbury Brown Twiss experiment, which is a HPT interferometer, which is basically the second order correlation. So I will briefly discuss about some of the developments, how one characterizes the light. And the essence of doing that, one uses something called the coincidence counter. And I will discuss about something about the coincidence counter we have developed at IIT Jodhpur. Followed by that, I'll briefly talk about the entropy associated with the various light sources. So basically one of them we did here as an experiment is a von Neumann entropy of the various light sources. So I will discuss about that. Followed by that, the MPPC or something called the silicon PM, which is a photon number resolving detector. So we initiated some of the experiments in this direction. So how to go about it and what it's right to convey, how to look at this, what is the advantage. I will talk about that. Also, another one of the interesting thing is something called the balanced Homodyne, which is basically look at the Wigner function of a given state as an experiment. What are the essential ingredients to build such a thing and how to look about it. Even though we have not completed an experiment, but that is quite a good kind of a learning curve we have here. And I will briefly discuss about that because Wigner function is a very interesting. Okay. So is my slide is changing? I have now changed the slide.
Yes.
Okay. So I am in my the third slide from the introduction. Various quantum resources known to us at this moment are the predominantly known to one is the nitrogen vacancy NV center in a diamond, which is on the top. I hope my cursor is moving. Which is on the left-hand side, top left-hand side. Especially with the various lasers, etc., development in the past 2 decades or so, one is able to generate the entangled photon. So here, one of the picture which is well known depicted by QIQT group, and most of us users is a CW laser. One uses a 405 diode laser, and using appropriate conditions, one is able to generate an entangled photon. But here at IIT Jodhpur, of course, we are also producing entangled photons using UV source of a pulsed laser. I will come to that at a later stage. Additionally, various colleagues, both in our country and abroad, NMR is also used as a source, and also SQUID, basically in TFR and IIC Bangalore, and of course the various other research group uses this also as an entangled source. So basically, these are the 4 broad category one can say the quantum resources. So why one looks at the quantum resources is basically because one can do the quantum teleportation, which is on the top left. At the bottom, the quantum secure communication, which is well known to, especially when you want to, nobody should peep in your conversation or get into the message to have the secrecy associated with it. And additionally, super dense coding, and also previously the speaker was speaking about the quantum computing, annealing, etc. So which is basically the various resources which are currently available. Some of them are open to all, some of them are of course restricted for the various users. So the application includes like the LIGO uses something called another special kind of a light, which is a non-classical light, which is a squeeze states, which is to see the gravitational waves, which is on the top. At the bottom, you have the QKD between the various countries are able to establish the quantum key using a satellite QKD. And also on the top right, you are able to see, bottom right, you are able to see the parametric down conversion, which I will be speaking about. So the application includes QKD, the quantum radar, quantum teleportation, and quantum computing, or some of the applications associated with the quantum resources of the non-classical state, and your classical light does not provide, and it has its own advantage. And further, also recently, various like boson sampling, etc., which are also in this direction. So how one produces the non-classical state is basically you are creating a hole in a number distribution, or something called the hole burning, or a finite dimensional quantum states, or the quantum scissoring. So you truncate a certain series, or also in realizing non-Gaussianity operations like photon added and photon subtraction. So some of the groups in Bellini, etc., in Europe, they have done some of the experiments. The bolded, the entangled state by a parametric down conversion, where I will be speaking mostly on, and some of the things in the progress. And in addition to that, as I conveyed, the squeeze state is also another one. Generates various kinds of squeeze states in terms of number, in terms of polarization, etc. So one uses various nonlinear optics or the fibers to generate this kind of squeeze states. So most of my thing today would be on the entangled states from the experimental point of view. So how one produces the parametric down conversion is basically here, which is you take a Shor FM2 laser, or a CW laser, depending upon the resource availability. In this case, we use a 1030 nanometer, which is a femtosecond laser. After something called the harmonic generation, one produces the UV photon, which is at, you can see, which is at 343 nanometer. And this UV photon is produced by a typical second harmonic, and combining the second and another crystal, one produces a third harmonic. It is called the THG. So this UV photon passes through a crystal, which is basically another second harmonic crystal, but in an inverse way. So you send a UV photon and you produce a photon in the red, or in some cases near IR. So such a thing, you do not have any classical counterpart, and you say it is a quantum resource. So which is here, experimentally one does is what is known as the Polarization-Entangled. So most of the work here at IIT Jodhpur are looking at is the Polarization-Entangled states. So the parametric down conversion process, which is the inverse process of the second harmonic generation, and here one produces the entangled states in both the arms, which is Polarization-Entangled, and the D1 and D2 are something called the single photon detectors. Basically, this process is a very, very a weak process, or I would say of the orders of, suppose you put 10 power 10 photons, you produce one. So the probability of producing SPDC is very, very small. So therefore, one uses a very sensitive detector called single photon detectors. Okay, and when the light falls on the single photon detector, it produces an electrical pulse, and that you give it to a coincidence count and or a coincidence counter, where the coincidence counter is the essence of the electronics here, where when a light falls, it produces an electrical pulse as an output. The arrival of the electrical pulse output is called the timestamp, or sometimes it is called time to digital converter, or TDCs. Okay, so we have developed here a couple of TDCs from the commercially available certain electronic circuits. So one typically produces like 400, you can see here at the bottom, so the femtosecond laser is can be operated at different repetition rate. That means you can operate per second like 100K or 1 megahertz. So that means the UV photons will be produced at this rate, and per pulse, per individual optical pulse, you might be producing close to 40 to 400 photons, which is written at the bottom, by using this BBO, which is a nonlinear crystal. And here we are doing something called SPDC. I will briefly explain SPDC for the benefit of everyone. So you can see here, this is a commercially available, but what we have done is you use appropriate optics and electronics to record this. At the bottom, you can see before doing the coincidence count, you have to get the image of the parametric down conversion process. So one has a type 1 and type 2. I will discuss that shortly. And at the right of that, you can see a black and white figure of a 2 circular rings, which is a type 2 SPDC. The upper ring is a, the upper ring is a one particularly polarized light, or it would be a vertical. The other would be the horizontal. The intersecting points are called the entangled points, or the entangled photon generation, which is a cone which is coming under certain conditions that I will speak in the next few slides. So typically an SPDC process is the inverse of the second harmonic generation. Second harmonic generation one can even explain from the classical fields, which is basically the polarization effect due to the interaction of the electric field E square, which is happening. But in the case of parametric downward conversion, you don't have any classical analog, so that is why it is a quantum. And this, lower frequency, a lower wavelength or a higher frequency photon decaying into a lower in frequency or higher in the wavelength is basically the entangled photons. And these entangled photons, you can have a various entanglement type. One can be polarization, other can be a mode, frequency, etc., or the energy time. One can have a various combinations. But I will speak about only the polarization entangled. So before, how does the entangled photon get generated is basically the certain conservation, well-known conservation laws. So both in terms of momentum and as well as in terms of the energy. Because of the lack of the time, I will speed up, and if any stage, if someone wants to stop, kindly stop. So one uses something called the birefringent crystals. So some of the examples are quartz, BBO, etc. And also one can use the modern crystals like quasi-phase matched, or something called the periodically poled, which has a higher entangled photon generation or higher nonlinear properties. So the typical equations which uses here is basically in the case of type 1, the extraordinary, you can see the second equation. So generally you have to conserve the, in the case of the birefringent material, both in terms of the polarization sphere, both in terms of ordinary, extraordinary ray. So in the case of type 1, the extraordinary ray decaying into ordinary, two ordinary daughter photons, which is called the signal and idler. S stands for signal, I stands for idler. So that's how one produces. In the case of type 2, which is here, the daughter photons are mixture of, you can see here, E and O ray. So that is basically you have the combination of either vertical, horizontal, or horizontal, vertical, vice versa. So here one calls it as based on the kind of geometry one uses. It is sometimes it's called degenerate, non-degenerate, etc. So I will skip this because of the lack of the time. If someone wants, I'll come back to here. So here appropriately by doing the phase matching condition, which is the essence of doing this, one produces this, the entangled photons. So you can see here in the case of the type 1, you create a single cone. In the case of type 2, two cones, and each one is differently polarized, and the intersecting point, which is green in color, is basically the entangled photons. Of course, in the entangled photons here, you may have a correlated as well as the uncorrelated photons could be together. And this is well known to most of us, and which is the Bell inequality. So one has to prove the given source, so the generated entangled photon is a non-classical one. So if it is less than 2, it is a classical resource. If it is more than 2 and less than 2 square root of 2, it is a quantum correlated, and the maximally entangled would be 2 square root of 2. So one uses the various combination of the S parameter, which is well known, using the various combination of the half-wave plate and the quarter-wave plate. One gets the Bell parameter or the S parameter. So this is a typical snapshot we uses. To watch this entangled photon or the ring, one uses the device called the EMCCD, which is on the left-hand side. Here you can see here the two rings. By changing the angle with respect to the incident photon and the nonlinear crystal, you can generate different kinds of collinear and non-collinear geometry. The amount of the light seen at the intersecting points is based on certain kinds of a back calculation based on the quantum efficiency. We say it is close to a femtowatt, which will be about, I think, close to 80,000 to 100,000 photons at this given wavelength. So here is the typical snapshot of the S parameter or the CH violation one sees, and one can see here we have done it for the classical light, which is 0.02. As usual, the experimental one has to struggle to get the to violation, and we are in the process. So initially we did it with the open air, which is basically you just to do it without any fiber. We are facing some problem, and now we are switching to something called the single mode fiber. So one takes care of all this optics, alignments typical in any given optical lab. And of course, one has to worry about the electronics, which I will, the coincidence counter, which I will be speaking about in the next few minutes. So this is how one sets up the various polarization, etc., on the path of this entangled photon or the intersecting point. So in order to look at what kind of photons one has generated, so way back in the early 1950s, the Hanbury Twiss experiment or the second order correlation or the G2 function, which is to characterize the different light sources. So one can see here a typical setup of a light source and using a beam splitter, and which is a 50-50 beam splitter, and you put a sensitive PMT or a avalanche photodiode or a single photon detector as a detector at the tumor arm of the interferometer. The output is given to a coincidence counter. So one can characterize various light sources using this method, and especially one can see like the Poissonian, which is a coherent source, and super Poissonian, which is a chaotic light or a black body radiation, and also these are Poissonian statistics one can see in certain non-classical light sources. So here, the developing a coincidence counter is a challenging job, and of course, given the resources, one can buy a commercial one, but which is quite expensive. So what we have generated is we have developed a coincidence counter based on something called the field programmable gated array FPGA, which is a kind of a modern most of electronic circuits are built on a chip, and of course you develop certain additional circuitries, and then you can see here a 4-input the coincidence counter, which will tell you the arrival of the photon in terms of something called the timestamp or time to digital converter. So by knowing the timestamps between the two different arms of this, either the Hanbury Twiss experiment or in the SPDC, you can get the time arrival of the photons, and that is converted, and then you extract the information among the correlations among the photons. One of the master student and a PhD student, they have developed our own, which is basically everything is developed in-house, which is a graphical GUI, which is basically a graphical user interface. So depending upon the different experiments, one would know that what kind of, say for example, certain experiments, one would like to see a timestamps within the very short intervals, can be of the orders of picoseconds. In some cases, one would like to look at it at a few nanoseconds to tens of nanoseconds. So if you have your own coincidence counter, your own the interface developed the softwares, then one understands the flexibility of doing things is at your hand. The additional coincidence counter also, which is commercial, these are all very, very inexpensive, which is close to 40 to 50,000. Of course, one has to develop cross-check with various other known resources, and one has to do a well-known a signal a resource. One has to check that indeed whatever you are getting is correct. The another commercially available, which is one can buy, but one has to develop the various peripheral electronics, is the something called GPX2, which is an inbuilt evaluation board, which is here, which is shown here. Again, this is a 4-input, and again, we developed our own electronic circuits. So you can see something called a clock pulse, and then the stop pulse is basically coming from the single photon detector or an avalanche photodiode. And you can see here the kind of one has to get back, or one has to, from the data acquired from this time to digital converter, you have to convert something called the real timestamps. So that is slightly a cumbersome process, but one learns it by both by trial and error and some kind of a consistency check one does, and then one has developed. So I'll speed up this. Again, we have developed this inexpensive one, and we have carried out various for the 2 different light sources. We have done the Hanbury experiment. Here is the essence of it. In some cases, if your optical pulse is not straightforward, one uses something called the pulse shaping unit, or CFD. CFD is nothing but a constant fractional discriminator, because you want to eliminate the noise which is coming from various surroundings or in a given electronic circuits. So I'll skip this. So, but one can with the various readily kind of available and understanding the circuitry, one carries out the experimental layout. And I'll just quickly show using the Hanbury experiments we have done with a laser for the coherent light source, the G2 tau would be a constant 1 for a very long time delay. So the y-axis is G2 tau which is a second order correlation function at a different times. The x-axis is basically the time difference, which are the first 2 graphs. And on the right hand side, what you are seeing is a normalized one for a fluorescent emission. So we took one of the Rhodoman 6G and then passed it across a broadband filter. And you can see here at when tau equal to 0, you see the maximum. This function has to be normalized, which is we are in the process of doing it. But basically, the super Poisson would be a tau equal to 0 would be the maximum, and then it would fall off. That is what we are seeing. And also using various the electronic circuits and the timestamps, we calibrated our this called the TDC, which is the jitter is 22 picoseconds. So that means the arrival of the photon if it arrives at time X, it would have a plus or minus 22 picosecond, and the company claims 20, so which is reasonably good. So this is the essence of the most essential part of when you are doing the entangled photon, because the coincidence counter is along with the single photon detectors of essential. So another way to look at the light is basically looking at the von Neumann entropy. So I will not spend time. So by looking at the various polarization purity of this, the H and V basis and the diagonal and the anti-diagonal basis, one writes the von Neumann entropy as minus trace of phi log 2 of phi, and one does the various projective measurements. So here in this experiment, what we have done, we have used the CCD or an EMCCD array. Each pixel is a photodetector, and we looked at the projective measurements both in the horizontal, vertical, and diagonal and the anti-diagonal. That means cross and the anti-cross basis, and right circular and left circular, by using the appropriate half-wave plate and the quarter-wave plate, and we looked at this entropy. So continuation of the same slide. And here is a typical experimental setup looks like. So you have a light source, and then you pass it through, because the EMCCD is very, very sensitive. So you attenuate the light, you use the narrow band filter to avoid the various background light entering. And then you use the half-wave plate, you can see here, the quarter-wave plate, and using the polarizing beam splitter, the various projective measurements, and you simultaneously take all the combinations, or sometimes it is the Stokes parameter. So you record it on this EMCCD, and it is grabbed by a computer. And here you can see on the right-hand side panel, what you can see here is you can also make combine few pixels and make a super pixel. So we have done combined 4 pixels or the 2 pixels or a single pixel. So then it is called the binning, those who routinely do this. So by doing so, we looked at the 4 different light sources, like a laser light, LED, and a dye, which is a similar like fluorescent emission, which is coming from one of the dyes, what I mean, and then the SPDC. So you can see here, as the binning increases, we are able to see a much, much better response on this, both in terms of von Neumann entropy as defined earlier, and also the square of the sum of the squares of the magnitude. And similarly, we also looked at the spread of this both for the on the left-hand side for the different light sources, both in terms of von Neumann entropy as well as the S1. So the laser being the which is close to 0, and the spread across is much higher for the SPDC, which is quite understandable from here. So one way to characterize the light is using the polarization technique, and one can imply or one can characterize using this von Neumann entropy. So coming back to, so once we understand both in terms of the electronics and or the coincidence counter and also the projective measurements, both in terms of the selective polarization, because since I'll be speaking mostly about the polarization entanglement, I'll go to something called the quantum state tomography. With we would like to use this femtosecond laser to produce the various higher order entangled states, both 2, 3, and 4, which are in the process. So the quantum state tomography, basically one does the various projective measurements across the single photon detector by using the various combinations of this half-wave plate, quarter-wave plate, and a linear polarizer. Sometimes it is the Glenn polarizer, or sometimes one uses something called the polar code, which will allow one particular polarization. Suppose if it is marked like this, so it allows this particular polarization. And the output of this fed into a the light is fed into a single photon detector, and then the output of this taken to a various combinations of the coincidence counter as discussed earlier. So the state tomography, one would like to reconstruct the state one has generated. So so if you assume that the given state is an unknown state, and one does the various projective measurements using this various combination of the polarizers, and one gets the tomogram by using the experimental data, and from there one try to construct the density matrix. But the issue of the density matrix, you can see here various photonic states. We have again used the various bases like HH, or you can see here, which is on the right hand side, the horizontal and vertical, right circular, left circular, diagonal, anti-diagonal. One is able to reconstruct by using appropriate the coincidence projective measurements. If it is a 2-qubit, it would be a 16 4x4 matrix. If it is a 3-qubit, it would be 8x8. And if it is a 4-qubit, it will be 16x16. So one can develop one can get from the experimental various projective measurements the density matrix. And this, which is able to allow here, which is basically the state tomographic technique. But some of the drawback of the state tomographic technique, because of the problem with which one might end up getting certain unphysical matrix, because the polarizer you want the kind of what you call it as a contrast ratio you will not get. You will not have the reflectivity may not be perfect. The interference filters which you use may not be very good. So all of them will contribute to a certain kind of variations or the fluctuations in the statistical fluctuations in the observed experimental data. Even like as I said, different the time to digital converter or the electronics adds to the contributing to the various statistical error. So from the tomography which one gets experimentally to get a physically known, one uses in this domain is called the MLE, or the maximum likelihood estimator. So from a unphysical density matrix to construct the physically known density matrix, one uses the MLE. So here MLE one uses something called the cost function. So locally again the students they have developed, the graduate students and the master students developed the MLE for the various 2, 3, 4 qubit. So the density matrix from the experimental data to you get the closest or a known state by using this MLE technique, by using the appropriate cost function. And so here we are able to do it for 2, 3, 4, which we have developed in-house, which is, and we cross-checked with some of the openly available resources. So one constructs the photonic state using this MLE technique, and which reasonably works fine. So you can see here, so some of these things, and we have used a 2-stage optimization to get this MLE function. Of course, in principle, one can expand this, but of course, it becomes complicated more and more, and those work. So to generate the highest state entanglement, one uses the initial 2-qubit entangled states, and using appropriate, you can see here a 3-qubit. By using 2 different combinations, one can generate a W state or a GZ state. So one uses the various polarizing beam splitter and normal beam splitter, half-wave plate, and a quarter-wave plate. Depending upon the state you want to generate, either a W state or a GZ state, from the 2-qubit one can do. So we are in the process of developing this. We have acquired appropriate optics, detectors. As usual, one has to construct on a breadboard on your tabletop and try to do this experiment. So which is ongoing effort. So the state you have constructed, indeed, to know this, as the state becomes more than 2, it is a bit complicated. So one uses something called the Wigner operator. So from the density matrix, as explained, one can use this Wigner operator so that you don't do all the projective measurements. One can do a certain projective measurements and conclude, indeed, treat it as a Wigner. Indeed, what you have generated is indeed an entangled photon or a non-classical state. So the Wigner operator for the W state here, it is written. So this is for a genuine to detect the genuine multi-party entangled states. For a pure state, close to that, W state equal to alpha into identity matrix minus kit psi bra psi, where is an identity operator. Then similarly, if for the W state, the trace of W of kit psi bra psi should be 0. That guarantees the multi-party entanglement. So we will be employing, we have chosen certain states and certain projective measurements so that the Wigner operator can be handled. So similarly, the first two are in this slide is basically for the 3 qubit, and similarly, Thomas, my graduate student, who has developed similarly for the 4 qubit, which we will be employing for this. So the lack of time, I will skip all this, but one can use appropriately Mathematica or appropriate the methods to do this. And in summary, one can develop the required witness operator to see a multi-party entanglement, and one can confirm indeed the generated states are, of course, the multi-party states are 3 qubit or your 4 qubit entangled states. So I'll skip this. So the little more complicated is how one generates. We will be employing this this one. Basically, it is a 4 photon. Here, basically, when the laser goes through here, the blue light, which is a UV light, and you reflect it back. So you produce 2 SPDC here. I hope my cursor is moving. And when you bounce back the another one, you again produce 2 qubit entanglement by using this 4 arm of the SPDC and overlapping with the appropriately the polarizing beam splitters and the necessary optics. One generates a 4 photon 4 qubit entangled states. And similarly, as I explained, one can use a certain projective measurements. Otherwise, one has to be a 16 cross 16, very, very complicated projective measurements for this to get the density matrix. So we will be employing this, and as the things progress, so that is the objective under this DST supported quiz proposal. So I'll come to another part, which is recently one not only uses a single photon detector. There is another kind of a detector well known in the high energy physics, which is called the silicon photon multiplier, or SIPM, or something called the multi-pixel photon counter, depending upon which company or which domain one uses. So basically, this is a photon number resolving detector. So a photon number resolving detector is, suppose if in a detector, if X amount of or N number of photons are falling, it is able to resolve, one should be able to resolve this. So both the commercially available photomultiplier tube or the single photon detector does not do this. So you have two kinds of photon number resolving detector. One is this SIPM or the MPPC, or the other one, which is a pretty expensive, which is a superconducting nanowires, which is exorbitant cost. So this SIPM or the MPPC is basically a construction of multiple pixels of a single photon detector, but it is kept in an array. And when your photons falls on any of them, or even one or many of them, it will give you an output, and the output is proportional to the number of photons. So you can see here at the bottom of it. So depending upon the output voltage produced at the output of this SIPM, one can correlate the amount of the photon in. But of course, one has to be very, very carefully, because here you typically it is able to resolve from few photons to hundreds of photons, and one has to take a very large number of statistics. So one has to attenuate the light. You can see here on the left hand side, and you record this by using something called the high-speed ADC, because you have to take large number of data and then get back reconstruct the photon which has fallen. So basically, you can do it under the Fock basis. Even in the previous speaker was mentioning something about this. So similarly, one can use this photon number resolving detector to construct what kind of number of photons based on that probability one can reconstruct. Of course, there are various noises will be there, and also there will be something called the crosstalk. One can see a little in this is by this, which is shown at the bottom. And also the other two well-known groups which have done is a group Kalashnikov from US, and there is one Israeli group, Silberberg. He is from Wiesmann. He has also used this and shown. So this has to be kept at very low temperature. So some of them inbuilt, which are kept at something called the TC cooled, which is typically minus 10 to 20 degree. If you get it from the manufacturer, they make it. Otherwise, you build your own TEC. Keep the chip on this and send the given light source. It can be a laser or it can be a broadband, like whatever I've spoken earlier, even an attenuated or a weak coherent pulse, or it can be even an entangled photons. So based on this here, right-hand side, you can see, yeah, we have kept it inside a blue color cap and my finger, which is pointing out the detector. So when there is no light also, you will see some kind of output recorded by using this ADC, which is a fast ADC. These details are again depending upon what we would like to see. One buys this, which is suitable to this, because you have to be very careful. The output of the minimum photon would be something like 20 to 30 millivoltage. So accordingly, one chooses appropriate ADC and the speed with which one occurs. So we have looked at when there is no light, that means completely you put it a dark count, and you get this here, you carry it for a few milliseconds or few seconds, and it occurs in the rate of megahertz. So even if you do it for a few seconds, it becomes close to 10,000 pulses or individual pulses, because for every photon hit, it converts some kind of an output pulse you see here. And one of the students, summer student, Aditya, he did the program for this, and we have developed this. So one puts it under different histogram. One keeps it like, suppose you get X number of millivolt, either it can be a noise, or it can be 1 photon, or it can be 2 photon. So here for the dark counts, we have done it, or a background, we have done it here. For a short acquisition, you see like this, you don't see a higher number of millivolts. But when you pass it through a fluorescent light, through appropriate pass it through interference filters, what you see is, you can see here the large number of the photon height. The height is proportional to the number of photons. Okay, and on the top right-hand corner, you can see it has a kind of a pulse width. It produces typically of the order of 30 to 40 nanosecond. So each hit produces at the output of this SIPM or the MPPC, pulse width, which is varying from nanosecond. Sometimes you may have also a double pulse, so one has to do a selection of this pulse height and the width. One has to do a very, very careful filtration to do this. So one writes a kind of a Python code. Those who are the young giraffes or the summer students, they do it very well. So we acquired a lot of data, and again here you convert this into the pulse heights. The objective here is, so after doing some amount of all this filtering out, you see the pulse height versus the number of events. So here, which is the experiment is ongoing, it is not concluded. So one would like to see, is it a kind of a state what you have generated is something like this, or is it some kind of a Poissonian distribution? One would like to see where the x-axis is the number of photons and the y-axis is basically the probability. So one has to convert from this output voltage, or in terms of the millivolts, the number of events you have acquired, to the different, the photon number probability. So this is again ongoing work. Even this can be introduced at a master level if someone is interested, because it gives a good idea of how to handle or how to visualize a Fock state or even a Gaussian distribution. So I will, the last couple of slides would be on the very interesting thing on the balanced homodyne detection, which is, I hope I have another 5 to 6 minutes. Hello?
Yeah,
Yes.
you have time. Please go ahead.
Okay. So another interesting way to characterize the light is something called the homodyne detection, where here one tries to get the what is known as the quadrature measurement one tries to do. So in the balanced homodyne, you have, which is basically using a beam splitter, kind of an interferometer. Here you use a local oscillator, which is slightly higher in intensity, and the signal, which is in a 50-50 beam splitter, you put it, and what you try to get is you try to measure the difference in the current. One would be, one of the photodiode would be the forward biased and the other would be the reverse biased. So the difference in the current is related to what is known as the quadrature measure. So here at the bottom of this, the challenging thing here to do is to get the phase information corresponding to the current difference measurement, which is non-trivial. So in order to do that, the phase measurements are done by very precise way, because the wavelength, if you use any light, which is even from visible 350 nanometer to 600 nanometer, which is mostly the visible, and then you have IR, which is very, very small. So doing a displacement or adding a phase information is quite challenging. So one uses nowadays, which is readily available, something called the piezo stage, which moves in terms of the nanometer. So what I have shown here, a red line, which is basically by moving in a Michelson interferometer, we want to calibrate the movement of the piezo stage, which moves in nanometers of 6 to 20 nanometer per each step. So in a Michelson interferometer, one knows that, suppose in a BSc experiment or a BS experiment or an undergraduate experiment, when you move the stage, you will count the number of distance moved, and one moves by hand, therefore it is very coarse, and one sees the amount of the collapse of the Michelson interferometer correlates with respect to the wavelength. But there you just do it by a large number of counts and try to estimate the wavelength. But here we want to have a precise information of the phase which is being added at the two arm in this across the beam splitter. In order to do that, one has to be a very, very precise controlled way. So this piezo stage gives you that information. So we have calibrated a piezo stage for a movement of close to, like you can see here, close to a kind of the amount of the data, what we call it as a kind of a millisecond. So you acquire data are different because I don't have a control. But what I know is as the interference fringes moves, if I get it between the two, the maxima intensities that corresponds to one path length. So the data acquired is correlated to the amount of the movement or amount of the data acquired. Therefore, I can correlate each step. The difference in the current measurement is correlated to the path difference introduced in the both arms, both in the signal and the idle. This is the challenging task. So now we more or less developed our own electronic circuits and then calibrated the arm of the interferometer. So the balanced homodyne gives you the quadrature or the known state in the phase space. So this is the differential current circuit, which is developed. And one introduces the two similar photodiodes and measure the difference in the currents. So the Wigner function, which represents the state in the phase space and which is the quasi-probability, and one of the readily available is, since it is, if it is a negative, we know that indeed the state you have created is of course the quantum state. And of course for things like various squeeze states, etc., also one uses this. One can also see a coherent state using this Wigner function. So with the calibration and then the kind of the acquisition is the challenging thing. So more or less, we have concluded soon. Again, we will be doing in the summer some of the experiments to reconstruct the Wigner state. So here one reconstructs by using something called as the marginal distribution from the quadrature and the phase data, which we have occurred as I explained, and appropriately doing this inverse Radan transform, one gets the quasi-probable state. This we have taken some random functions and tried to see the program is working. We have calibrated this. So one has to, the challenging thing is you have to fill each individual photodiode. You should not miss the photons. So the coupling of the light into the active area here is very, very challenging. And I would like to point out the detectors used are not at all very, very expensive. So say, for example, single photon detector is something like 2.5 to 3 lakhs. The detectors, which are the photodetectors which are used here, is a non-single photon. A photodiode will do, but it should have a large quantum efficiency. And that large quantum efficiency should be as close to 80 to 90%. So sometimes one uses something called the pin photodiodes also. The photodiodes are very, very cheap, something costing about, if someone is interested to, I can give some of the info related to that. The generic information, the circuits one develops is you can change the different wavelength, even if you want to do it in the infrared. One can try to do, because today 1550 is very easily available, even inexpensively. So this is how you do it. So the difference in the current, either you give it to an ADC or a spectrum analyzer or an oscilloscope. So we have seen it across the oscilloscope by giving individually in the both arm of the photodiode, and we have checked it is working. We have calibrated this. So only thing is we have to very synchronously acquire the data and then complete this and try to reconstruct the Wigner function for various unknown states. So with this, I come to the fag end of my talk. So the planned activities, instead of concluding, since it is a developing work, so I don't conclude. So I basically say some of the planned activities in the days to come is the generating the higher qubit entangled states using the pulse laser and doing appropriate MLE to get to the close to the states we have produced. And one uses the various witness operators to understand and confirm the states as a witness you're prepared. The HOM interferometer is basically, which is, since we have calibrated the piezo state, my last few slides of the talk, we would be implementing, if you send only the 2 photons, they will go together in one of the check is you're very close to, what is known as a subpoisonant states. So the one confirms using with HOM. And various aspects of theoretical and experimental aspects are done, carried out at IIT Jodhpur in collaboration with my colleague CHSH Banerjee. So generation of the entangled photons also we would like to do, but within the lab or some distance, we will be doing this. As I told you, the Homodyne and getting the Wigner is very, very challenging, but this work is also in progress. Some of the things which is funded by QIQT, etc., which is on the part of the DST program, we are part of it. I would like to acknowledge both my colleagues at IIT Jodhpur, Subhashish Banerjee and Anirban Mitra from JIT Noida, and generous funding from DST, DRDO, and ISRO, various funding organizations help us so that they keep the investigation in progress. Without the graduate students, Thomas is a CSR fellow, Roy Philip earlier with us, and now he is at UTT Paris. Ravikant is an Inspire fellow earlier. He was a JRF under this project, UST project. Ajmal, who is a current JRF. Master students, Shiva Mageshwari is currently at Germany. Abhilash is an earlier master student who did some work on the quasi-phase matching of the periodically PPKTP. Because of the lack of time, I'm not showing. Because he's at Trinity College, Dublin. Pooja is again a master student. She tried to do some of the something on the quantum imaging she did on the theoretical aspects, and some of the continuing help from the summer students, even though I did not list all of them. Arun Sebastian recently did a lot of work towards this the circuits related to the Wigner or the balanced Homodyne, something related to what CMMR constant mode rejection ratio. So what kind of op-amps, how to do all this? Ram Yadav, he is from ISO Kolkata, who is currently with us for this coming 2 semesters. Rejo is another student who is coming today and from Cochin. So various students across contributing to this various aspect of me to learn some of the non-classical states. With this, I would like to thank and any questions, glad to answer.
Okay, thanks, Dr. Narayanan, for the nice talk. So let's now move on to the questions. Audience?
Thank you, sir, for a wonderful talk. I have a question. In the two types of this SPDC process, we have this phase matching conditions. So there might be like a situation where there would be a phase mismatch. So how will we deal with those problems? So that is the main question.
Okay, so there are various mismatch. Okay, I did not again because to keep the talk within the time limits. Okay, so let me go one by one. So the first is, of course, you might have followed. You can use any of the known second harmonic crystal, the inverse process you can do. So depending upon the kind of the light intensity, the focus, appropriate conditions, you produce this SPDC. But it is not straightforward. One encounters, there are 2 other kinds of a problem. in the nonlinear optics, because there are the birefringent crystal, you will have something called the walk-off also. So you have to compensate that. I did not have the time. So there is something called the spatial walk-off, and there is something called the temporal walk-off. If the thickness of the crystal is very small, say for example, like 1 mm or 500 micron, half mm thickness crystal, you don't see much problematic. But if the thickness of the crystal is pretty high, like 2 mm or 1.5 or 3, these effects are pronounced effects. So one has to be very, very careful while doing this. We do encounter sometimes, so we have to compensate it. We have to replace the crystal. So some of the things are well known in terms of nonlinear optics, which is available. So one has to do a very careful estimation of the various phase matching conditions. I hope I answered this question. If it is still some clarity is needed, I would like to see.
Yeah, it's clear to me. Thank you.
So some of the data, so one has to do a very, very careful check. So various, the refractive index data at the various, various sites which are available either in the optics or the condensed matter sites, because you get for N-ray, E-ray, O-ray, etc. You have to be, because these are all completely wavelength dependent. So one carefully looks at it very, very carefully and computes that and carefully does it. Yeah.
Thank you for your talk. I have one question. So,
yeah, sure.
What is the noise level in polarization parameters of light? Whether it is below the noise level in coherent light or above?
Okay, there is some audio noise level. Is it correct, if I understood correctly?
What is the noise? I mean, you are measuring polarization parameters of light.
Yeah.
And my question is, what is the level of noise? Whether it is below noise in coherent light or above?
Okay, the noise. Okay. So this is with respect to the von Neumann entropy or something, or generic?
It's generic. Right?
Okay. Okay. So typically, okay. Yeah. So here you might have noticed all the detectors are reasonably sensitive to noise. Okay. Even say for example, this EMCCD, you keep the what you call the chip, which is close to minus 55 degrees centigrade. Okay. So photon detector. So how do one define the noise? Okay. So as an experimentalist, what we do is the following. I will come back and connect it with respect to in other aspects also. So if you want to look at the noise, so what you do is in all this, be it a single point detector like a single photon detector or an array detector, you take the background noise and subtract it. So that means before start of your data, you don't send the light, and then you acquire something, and that acquire would have some amount of noise. Say for example, when we are doing the experiment, we block the EMCCD and take the data, and it will give you some value, some depending upon the kind of the temperature, as I said. Even if it is, we have kept anything, even whatever the specified, still you will have some kind of a noise, which is about something called, we call it as a count, which is about 700 counts. At the same time, when I send a laser, which will be about 1400. So that means that each individual pixel is twice the amount of the noise. I mean, that is a typical, okay? It need not be the hard and fast, but this is the kind of a thing. So if you say a noise, the noise also depends on the integration time, the interference filter you use, the temperature, etc. So one always ensures that the noise is much higher. In the case of, if you look at either, say for example, one can use this SIPM or the SPAT also for the noise level. There you look at the count rates, okay? So our count rates per second given by the company is close to 50 counts per second. So that means if you send a light, even if you don't send any light, you block the single photon detector, you will get 50 counts. But when you do an experiment, you get about close to 2,500 counts. So that means you are much, much higher than your noise level. I hope I clarified.
Thank you.
Okay, for the sake of time, I think we should move on to the next talk. So thank